Hello, my name's Keith. I'm the developer of the ChibiAkumas 8-bit bullet hell shooter for the Z80 systems, Amstrad CPC, ZX Spectrum and MSX. Now, if you saw my last video, I did a brief introduction of memory mapping on those three systems. I said at the time I was only explaining the simple things. I felt I hadn't really done enough on those systems and I wanted to do a little bit more. Also, I went into some detail of how the screen memory worked on the MSX. However, I thought it was a bit lacking of me to have not explained similar things on the Amstrad CPC and the Spectrum. So what I've done today, I've prepared some more demonstration files which will show us how the memory works on those two systems, and also I'm going to go in more detail on the memory mapping, the more advanced options that all three systems offer, so that anyone who's looking to develop or just looking to understand those systems will have more of an understanding of what memory mapping options they have and the more advanced tricks that they may do that might catch you out if you're looking at how the system's working and as understanding what's happening. So hopefully this will be interesting to anyone who plays the computers and wants to know more about how they actually work, or people who are looking to learn to program on those systems. So here's my my three emulators, but for starters we're just going to go to my LibreOffice spreadsheet here and we'll have a look here at this is the same chart as we looked at last time, but you'll notice there's been some more things added. So let's make a start. Now, the first thing I didn't cover is, last time I mentioned that on the Amstrad CPC, the system has its own settings that it stores in memory that I actually raise. Now, on the Amstrad, those are in this area here, and they use the top half of this bank from about A800 to BFFF. They reside in the top half of this bank here. So that's the Amstrad, and as I said last time, when I start the screen buffer, I actually raise those because I am able to recreate them by calling firmware functions to do that. So that's how it works on the Amstrad. The Spectrum has some similar settings, however they're in this area here and they're at the top half of this from about 5B onwards. Now, on this system, the Spectrum, the screen memory does not use the whole of this bank, so I don't know any way of clearing them and recreating them. I don't need to, because they actually do not use all of that bank, which is of course different to the Amstrad CPC, so they don't cause me a problem so much on the Spectrum, so they just stay there. So yes, it's worth knowing they're there. It's also very important to notice that they're just slightly below the screen memory, because if you make a mistake binary writing to the screen, you can actually corrupt the stack and things, and you can end up in all kinds of strange things going on. So it's worth bearing in mind that that's where they are. So, and then finally on the MSX, there is also some firmware functions, and they appear in this bank here. Now, a lot of the documentation, they start from F000 onwards. However, that's only the case if it's a system without a disk drive. If it does have disk drives, they will actually use more memory, and the exact amount of memory they do use can't, to my knowledge, be predicted. I can't tell you exactly what they use. As far as I can tell, they don't use anything below D000. They seem to use it something like from E00 onwards or less. It's very difficult to exactly judge it. So as far as I can tell, you're safe using anything below D000. So yes, it's important to know they're there. It's important to know these memory areas that you have to sort of protect or preserve, provided you are actually ever going to call the firmware again. If you no longer need the firmware, then you can just delete them, ignore them, do whatever you want, and it's a lot of fun doing that. However, with ChibiAkumas, because it's a multi-load game, I am actually using the firmware to reload the next levels from the disk, so I need to make sure the firmware has still got all the data it needs to be able to function normally. So I have to, in the case of the Spectrum and the MSX, preserve those variables. In the case of the Amstrad, I recreate them and then patch back in the current disk number and things, so that everything carries on the same way as it was. So that was something that it was important at this stage to explain. And it's also something very important that you do know if you're working with these systems, especially if you're using multi-loader games. So that was the first thing I wanted to explain. Now, another thing that I mentioned that the Amstrad CPC 128K has these 4 extra banks here, which is of course true. The CPC Plus has what you could consider to be a special bank, which is the CPC Plus ASIC memory. Now, the CPC Plus, for those who aren't familiar with the system, has it has hardware sprites. It also has more colours, and it has options for raster level interrupts and a few other clever options as well. These are things that the original Amstrad CPC could not do, and the way that they work within the system to a great extent is that you send a bunch of special commands to the system, and this new magic bank of memory appears in exactly the same place at 4000 as the usual ones, but this new bank appears, and then you pipe your data into it, and they will appear as sprites or as new colours and things like that. So it's a kind of a secret bank. It's slightly unusual, but that's how it works. Now this will come into something else that I'm going to explain, but I'll get to that a little bit later. Now, as well as I mentioned all the RAM banks last time, but I didn't mention ROM. Now, the Amstrad CPC has 2 ROM banks. One that will appear at the bottom, overwriting this area of memory, and that will be the sort of basic ROM, which does the sort of things that the CPC 464 will do. So it handles all the normal kind of things. But then the machines that have a disk system have another ROM, which appears at the top area here, covering up the screen, which may seem a little unusual, but there's something I'm going to explain in a moment, which will maybe make that a little more clear. But so if you want to sort of consider the areas that are not used by any ROM, then that only leaves you with these 2 areas here. Now, one of which is the bank that can be swapped to anything on the system, and then the other one is the one where the firmware variables are placed, and you will realise that the reason the firmware variables are placed there is because they are then available to all of the ROMs. So it all starts to, when you really start to dig into these systems and look at the sort of jigsaw puzzle of the functions and the limitations, it will all probably start to make a lot more sense as you see, well, this is here because this is there. If they were in the opposite places, something else wouldn't work. It all does start to make sense, and what originally looked like a ridiculous limitation will probably start to seem a bit more like a good choice, or at least that's what I found in a lot of cases. So, okay, we've discussed the ROM, we've discussed the ASIC variables for the CPC Plus. Now let's have a look a bit more on the memory banking. Now, I described that it was possible to bank in any of the 4 extra memory slots into position in 4000 here. However, that only explains 4 of the possible 7 memory banking options. We do have these extra ones here. Now, C0 is very plain, that's just the basic 64K all in normal position. Now, C2 is a bit of a quirky one, where all 4 memory banks of the main 64K are swapped with all 4 memory banks of the alternate 64K. Now, if you've not done any assembly programming, you probably won't realise this, but the program counter in assembly in the Z80 is the currently running memory location in the main 64K banks. It has to be in the main visible 64K just because it doesn't make any sense otherwise. Now, if you swap all 4 memory banks for a completely different 4 memory banks, the commands you are currently running are going to be changed. So if you were going to do this, then you would need to make sure that the program counter was going to sort of collide with an instruction that made sense when these new 4 memory banks were paged in. Now, as I say, the new memory banks will affect the program counter and will affect the Z80 processor. They don't affect the screen memory. The screen memory is always read from the basic 64K. So if you were to swap in those extra 64K banks, you could do lots of processing. You couldn't display anything to the screen without switching back. I think there's probably some great functions for this memory banking mode, specifically for swapping areas of memory quickly between the 128K systems, but from the 128K banks. But for displaying things on screen, it's probably not that useful. But it's definitely worth knowing about because it's a good option to have something like that. Now, the remaining 2 are quite interesting, or at least they appeared interesting to me initially, but I will explain why possibly they're not so useful. So here you've got C1, and you'll notice this has the normal first 3 banks and then RAM bank 7 at the top. And then the second one, C3, has the first bank is the normal one, the third bank is the normal one, but then RAM 1 and RAM 3 are swapped over. and then still RAM 7 at the top. Now, RAM 1 and RAM 3 are what is often used as screen banks. I don't. In ChibiAkumas, I actually use RAM bank 2 as my second screen, but most people, maybe I'm being judgmental, a lot of people recommend, and a lot of time you'll see banks 4 and banks 8 being used as the screen buffers, and I think possibly part of the reason for that is because then the firmware variables that I mentioned would be untouched. So you use this one and this one. Now, the reason I didn't do that is because that would have made it very difficult for me to use the extra 128K memory for getting data to the screen. But a lot of people do it, and you'll see if you use these hardware bank flips here, then your screen would be either here or here, depending on which page you were showing. And now the memory location is identical, even though the screen location, even though the location that the system is showing, because remember the system doesn't use this paging, the system always uses those basic 64K banks. So by using these memory banks, you can switch your data location you're writing to, and it will get to the screen buffer that the computer is not currently showing, and then you've got this 7th RAM bank always in memory here. Now this, as I say, this sounds great, but there's a killer reason that it's not particularly useful. The 464 has no memory banking ability, so it can't do this. It can't even swap RAM banks 1 and RAM banks 3. The original ChibiAkumas game, ChibiAkumas Episode 1, the original release, used these on the 128K system, but did not use them on the 64K system. The problem with that is if you're going to support 64, then you've got to do the other alternative. So really, you're just adding code that makes very little performance difference if you use self-modifying code and doesn't cover all bases. So I'd just suggest giving up on these. It's a nice idea, but unless you're doing 128K only, they really don't help you. Now, I mentioned before about the firmware will cover the top memory area, and I'm told that one of the main reasons these two options exist is because they allow the disk system to get to RAM bank 3 when this top area is covered by its firmware, which makes a lot of sense. I think that's a perfect reason for it to exist, because, as I say, it's not really that useful for actually screen buffering because it doesn't exist on the 464. Right, so now I've explained C1 to C0 to C7 here, which are the functions offered by the basic 128K system that most people have. Now, the Amstrad CPC is capable of a lot more memory. There are 4 megabyte memory upgrades, but they're a little bit unofficial. Generally speaking, 512K is the maximum the Amstrad CPC has, and it's very simple the way it works. You go from C7 and you just carry on all the way up to FF. So if you had a 192K system, you would then be presented potentially with banks C8 to CF, and now in theory they would mimic the first 8 banks. However, I'm told that because the extra memory banks are controlled by the memory mapper hardware that is provided with them, a lot of those unofficial memory mappers do not support the equivalence of C0 to C3. Now, you can be guaranteed they will exist on a 128K upgrade, but if you've got a 256K upgrade or a 512K upgrade, they may not work. So you could use CC to CF and D4 to D7 to access more memory banks on a system that has that upgrade, but you cannot rely on the fact that the C9 memory bank or the CB memory bank will do this strange flipping option here. You can't rely on it. Apparently, a lot of them don't. So that's something to bear in mind. I should say one thing that is very useful about C1 or C3 for that matter. As I said before, they bring in this RAM 7 into play at this unusual location, because all of the other memory swapping options bring the extra memory in at 4000 here. Now, if you remember, the CPC Plus data also comes in at 4000 here. So if you need to copy your sprites into the Plus data to do sprite animation, then all of your extra RAM banks here are out of play, whereas RAM bank 7 here is still very much available. So this is a great way of getting in a bit of extra memory to do your sprites. And in ChibiAkumas, the CPC Plus sprites are actually stored in RAM Bank 7 because it's just a great easy way of getting a small amount of sprite data into that ASIC bank for the plus sprites. So there we go. I think that covers that. Now we'll carry on for now on the memory banking, and we'll get to the screen displays, and I've got some demonstrations I've made which we'll have a look at later, but let's carry on for now. So the ZX Spectrum, I mentioned before about the fixed ROM in the bottom location, and I mentioned the screen memory and the buffering here. Now there is a more advanced function which I didn't explain. I made some comments that I found it very difficult that the ROM was at the fixed location at the bottom of the memory area here. And apparently I was not the only one who felt that, because when Amstrad took over the Spectrum, they wanted to bring CPM to that system, and CPM requires, I believe, into mode 1, which of course you can't use if you can't get access to those low memory areas to write to. So what Amstrad did is they added some more advanced banking modes which removed those restrictions of the original ZX Spectrum, and they took away that ROM completely. And here they are here. There were just 4 of them, and the first one has all of the alternate plus banks, all of the banks loaded in here, so it's entirely RAM again with no screen memory visible. And then the second one has 2 memory banks and 2 screen banks here. The third one and the fourth one you'll see here are very much like C2, C1 and C3 on the Amstrad CPC, that they have fixed memory with just the screen buffer that is visible in the memory area changing between the 2 of them. Now these would in theory look maybe useful to the game developer, however there is a very serious problem with them. The Amstrad, after Amstrad took over, they made 2 Spectrum models. The plus 2 black edition, there's 2 editions. There's one with a grey case which has a tape drive, that's the non-Amstrad one, and the Amstrad one which has a black case and a tape drive, and then they made the plus 3 which has a black case and a disk drive. The problem is they only represent about 10% of the active Spectrum users out there. It's a very, very small market. So basically, if you could use these, maybe they would help you. Unfortunately, so few people have these systems, you can't use them. So they're a curiosity. It's worth knowing them, and if I'm going to describe all of the banking functions of these systems, it's only fair I mention them. But as for a developer, unless you're aiming at a very small market, really you can't use them, unfortunately. So anyway, moving on from that over to the MSX. Now I mentioned the 64K of internal memory last time, and I mentioned the VDP memory, which is completely separate. So I'm moving on from that. What I didn't mention is the slot functions of the MSX. The MSX is a heavily upgradable system, and it works in this sort of slot mentality. Now, if you look at an MSX, the physical hardware, you will see that there's either 1 or 2 slots in the hardware for plugging cartridges in, and those are marked slot 1 and slot 2, and you can see them here. However, internally the MSX actually has 4 slots marked slot 0 to slot 3. Now, while I believe slot 1 and 2 are kind of standardized as being external slots, the internal function of the slots can vary very wildly depending on the MSX, depending on the manufacturer. So what I've done here is I've just marked a sort of hypothetical layout just for us to discuss, and to make it clear that what kind of thing you maybe could expect the MSX to do. Now, as I say, there are 4 slots, but each slot can be split out into 4 sub-slots, and this makes it even more complicated. So let's just sort of start off with a very simple example, and I'll try and break it out, and I'll try and explain it as best I can, because I have to be honest, and even though I don't really understand, I only understand the MSX slot switching enough to write the game that I wrote. I don't understand it enough to manufacture my own hardware or to direct address more advanced hardware. So this is just going to be a bit of a brief introduction, and will hopefully give people enough of an idea that they can start to do their own research if they really want to get into MSX slots, because it's a very complex subject. So you've got your 4 slots here. Slot 0 tends to be the internal ROM. Slot 1 and 2 are the external slots. And then slot 3 is often the internal memory. But as I said, you can't really rely on any of these things being true for all. You certainly can't rely on it being true for all MSXs. Now, it is possible, but not necessary, that a slot can be split into 4 subslots, and that those slots can contain other things. So slot 3.0 could be memory, but slot 3.2 could be ROM, and it will vary depending on the system. Now, when it comes to these slots being sort of in the system, the way they work is each slot will be able to page in and cover parts of the memory area. So you've got your basic 64K area here. It's split into 4 chunks, and so I can map the bottom chunk here to subslot 3.0's equivalent memory here. So this could be mapped to this, but this could be mapped to something completely different. This could be mapped to the equivalent area here, and then this could be also mapped to here, and so on. So you can bank in certain areas of the memory into the system. Now, one thing that you typically can't do with an MSX is you can map segment 4 here to RAM area C000 here, but you can't map it to here. I said typically because some systems have a memory mapper which does allow that kind of very advanced mapping, but only some of the MSX Pluses have it, I believe. I don't think they all do, but some certainly do, and it's possible for lower end systems to have it. But again, it's like I said before, you can't rely on it, so unless you're doing very advanced coding, it's best just to pretend it doesn't exist and just stick with the stuff you can rely on. Now, the slot selection is done by an out call to the ports on the system. Subslot selection is a little bit more odd. Now, if a slot has been expanded, which you can check an internal variable, which I can't remember the number of, but there's an internal variable here which allows you to check if a slot has been expanded. But when a slot is expanded, a register will appear at memory location FFFF, which is a kind of, it's like a virtual piece of memory that if you write data to it, that will reprogram that slot. Now there's a separate one for each slot because each slot will have its own hardware sub-slot manager built in. And so if you page in slot 3 and then send the command to this register, you can then reconfigure which subslots are active for slot 3. It should be pointed out, if slot 2, for example, is not upgraded, then this memory mapping register will not exist. I'm sure this is really confusing people. I apologise it confuses me, but as I said, I really wanted to explain in entirety how this works so that at least people could say, well, I've heard something about it. If you're interested in this, if you really want to get into programming on the MSX in detail, then please look into it more and hopefully you'll be able to understand it better. If you just want to make it work, feel free to nick the code from the ChibiAkumas game. I'll be making it open source. I've got a command that turns the ROM back on. I've got a command that turns all the memory on. That's all I do. I don't get more involved in it. But I just wanted to explain this slot-subslot concept because it's a clever concept that gives an 8-bit system the sort of PCI expansion kind of functionality. However, it is a little bit odd, and you do really need to understand it to be able to use it, I think. So anyway, I think that's about all I can sort of go into today. Just basically, you've got this sort of 4x4 slot-subslot mapping. Don't rely on anything being in a particular location. Memory could be in different locations. ROM could be in different locations. You can't rely on every system being the same because they won't be. So that's a bit about the MSX memory mapping. And now I've probably completely confused people. We'll move on and have a look at something a bit more fun maybe. So I'm not going to do any work on my MSX, so we'll just minimize this. What I am going to do is I'm going to show you some visual demonstrations on the Spectrum and the Amstrad CPC. So I'm just going to load a memory save state here. And we're going to load screen test CPC. Now, what this is just a very simple basic script. If you've not looked at BASIC before, I'll just very quickly explain it to you. So what we're going to do is we're going to go from memory bank C000, which is the bottom of the screen memory, to FFCF, which is the top of the screen memory, and then we're going to poke, which is a command that puts a number value into memory at the place we specified. We're going to put the decimal value 127 into every screen memory location in the entire screen range in a loop, and next just repeats the loop. So let's run this and we'll have a look at what happens, and I think if you've not used these systems before, maybe it's going to surprise you. So let's start it up. Now you'll see we're filling the memory, but rather surprisingly we're actually jumping 8 lines at a time, and when we get to the bottom of the screen we get back to the start. So what this means is you can't directly move from one line to the subsequently one line lower line in a sort of direct manner. You have there's some involvement involved, because you've got to work out where the bottom of the screen is and then kind of bounce back up. So you can see it's filling. Now that's the first thing to notice, but then the other thing to notice is the layout of the bits on the screen. Now I've poked the number 129 into memory here, and if you have a look at my calculator here, you'll see 129 here. So let's just have a look at this again. 127, I apologise, 127. Sorry, I did various demonstrations the other day, I couldn't remember which. So here's the memory, here's the byte map we used, and there's actually sort of 10 at the top here, which this calculator doesn't show. But you'll see that actually on the screen, all the bytes are filled, and the top one is blue. Now the reason for this is that the way the screen, the Amstrad CPC maps the bytes to the colours is slightly unusual in modes 1 and mode 0. Now in mode 1, a colour isn't defined by the 2 neighbouring bits in the byte. A bit will be a pixel colour will be decided by bits 0 and 4, 1 and 5, 2 and 6, and 3 and 7. Now that's kind of doesn't make a lot of sense, but let's just give an alternate example. If I put in 11110000, that will colour all of the bytes in colour 2. If I put in if I delete that and put in 1111, that will colour all the bytes in colour 1. And then if I put 111, get this right, there we go, and that will colour all the bytes in colour 3. So it's they've kind of split the byte in half, and then they're using each half separately. Now this just looked ridiculous to me at first when I saw it, and I think the logical reason for it is it makes no sense at all until you come to actually showing characters from 2-bit all the way, from 1-bit all the way up to 2-bit. Now if you look at these characters here on screen, these are actually stored as just 1s and 0s, and 1 is off and 0 is off and 1 is on, and it makes quite a lot of sense to fill when the colours are defined in this structure for doing those fonts, and I think maybe that's the reason for it. But anyway, it's important to know about the Amstrad CPCs. It does have 3 screen modes, and so if we run it on different, mode 2. So mode 2 is just black and white. So if we run it on this, it gives us more what we would have expected to see, where we've got this one missing pixel at the top of the screen memory. And then in mode 0, which is a 16 colour mode, it's even more complex. I'll just read to you how this one works. Now, the first pixel in a pair on mode 0 is apparently made up of bits 1, 5, 3 and 7. Now I don't know about you, but the middle 2 of those kind of seem backwards, so very confusing. I'm reading this off a bit of paper because it confuses me every time I see it. I really, you look at it and you just think, is that really correct? But yes it is. So now one thing I will just sort of let you know here, which is a trick I used, if you're struggling with your maths, which I do, if you're struggling with your binary to hexadecimal or whatever, I would suggest you either go to Excel or LibreOffice, because there are some great commands there's some great commands like bin to dec and dec to hex, and there's loads of really great commands. And what I literally had to resort to doing when I was starting to do the ChibiAkumas game, which uses mode 1, the 2-bit per pixel mode, I had this huge chart of every color that would come out from a binary option or a hexadecimal option, and vice versa. Well, if I want the first pixel to be color 1, the second to be 3, the third one to be 2, this is the hexadecimal value I need to pipe in. I wrote this huge chart, so it's worth considering using spreadsheets to help if you're struggling with your hexadecimal or with your binary or whatever. And the other thing to say is I would strongly recommend using BASIC if you want to quickly see whether what you thought would happen will happen. If you want to see what will happen if a certain value is put in, just put in poke and C000, 32, and you can immediately see here, my mouse isn't showing, at the top of that pixel there, you will immediately see that whatever you've just done will be represented. Writing a little program, or even just typing a few commands in, just to see how certain bytes appear in the screen memory, is a great way of starting to understand how the screen memory works, and just double checking that what you think you're trying to get the screen to show is actually what's happening. So I fully encourage that for people if you're like me and you struggle with your mathematics, or you struggle with assembly with hexadecimal, with binary, and with converting or addition of binary or hexadecimal. So yes, definitely use those if that helps you out. Now we're going to carry on now with a second example which I've made, and this one is actually an assembly language example, so I'll just drag it in here. So I'm only going to this isn't really going to be an assembly language tutorial, so we'll only briefly look at the contents. Basically all we're going to do is we're going to go from the top of the screen memory again. This is the length of each line, and then we're going to fill each line with the byte value of the line number. So line 0 will be filled with zeros, line 1 will be filled with ones, line 2 will be filled in twos. Now if you remember before, I said you can't go directly to the next line in a sort of linear fashion, you need to calculate it. And so what I've done here is I've actually copied this command getNextLin, which is a command, I've just pulled this straight out of the ChibiAkumas game, and this is the version that I use in the game itself. And you'll see all it does is it adds 8 to the top to the H value, which equivalently adds and 8000 to the HL value. And that's the equivalent of moving down one line. Now the problem is if you go over the bottom of the screen, you've got to cycle back up to the top, and that's what the second part of this does. Now you'll see this is this weird label here. I use self-modifying code so that when I'm showing the alternate screen buffer, this code will reprogram and it will continue to work wherever the screen is. So that's but if you don't understand that, just ignore it. All I'm saying is this is going to go through the screen memory and it's going to fill each line with a byte. So let's compile it. There we go. And let's call 8000. This is going to call this memory area here, which I've just compiled to. And you can see that was very, very fast. And that's the beauty of assembly over BASIC. It's not just twice as fast, it's 10 times as fast or 100 times as fast. It's very, very fast. So here you go. Now you can see we've filled all the mode 1 bytes with the equivalent line number. Now let's go to mode 1 where maybe that will make more sense. So there we go. Now I said before the pixels don't kind of map in the way that I would have expected to them. They don't map in the logical way that the MSX does. But you'll see here now the first few lines go from going from the byte being entirely sort of black or blue in this case, entirely zeros, to being filled with the first color. And this is what I described as being the first few bytes will set the first color, and then as you start adding to that, you kind of start mixing in the second color. It's slightly odd, and it really surprised me, and it wouldn't have been what I would have chose, but as I say, I suspect there is a good logical reason for it. Anyway, I think there we've probably had a quick look at how the bytes are mapped in memory, how the screen is laid out, and also how we can get around the problem of moving around the screen memory on the Amstrad CPC. So I'll just get the Amstrad CPC out of the way here, and let's get the spectrum in, and let's have a look. So here's our spectrum here. Actually, let's load this one in here then. So I've got here, hopefully we can load this screen test here, and here we've got the equivalent command here. Now to my knowledge there's unfortunately no way of showing hexadecimal, storing hexadecimal values in basic programs in the Spectrum, so let's just have a look at these. 16384 in decimal is 4000 in hexadecimal. Now that is the start of the screen memory area, and the screen memory actually goes up to 5B00, but does not include that because I made that mistake and crashed the system. 5B00 is actually the start of the firmware variable, so when I wrote to it, it crashed. So don't do that. So the actual last byte of the screen memory is 5AFF, and if I've done it right, that is actually 23295. So that's the area we're going to fill. Now let's see what happens. I think you'll probably find that it's fairly logical at first, but maybe it'll get a bit more interesting later. So let's have a look. So let's run it. And you'll see we're now filling 1 pixel here. And 129, it's actually 2 pixels, I apologise. So 129 is, if we'll just get to our calculator here, 129 in binary appears like that. And if you look, we've got 1 pixel at the left here, and then 1 pixel at the right here, and then 1 pixel at the left here, making it look twice as thick. So I think you can see that looks pretty much how we'd expected. But you'll notice it's filling in thirds. And it's kind of strange because it's jumping down in lines of 8, and then it's jumping back and starting to fill in the gaps. And it's filling the screen in these 3/3 chunks, which is very strange. And we will discuss it, and I'll give you my theory as to why it's doing it. But so you'll see we're filling the screen here, and you probably think, oh, okay, that's a little bit odd, but generally it's about the same as the Amstrad. But you'll see something more interesting will happen soon, and maybe you can guess what it's going to be if you know how the Spectrum works. But so we've now filled the screen bitmap, and look what's happened now. We've started colouring the screen, because immediately after the screen bitmap we've got a colour area, and you'll see that is actually mapped in a logical way. It's in a linear fashion, which would have ideally be how we'd like everything to be done, but it's not. Now you'll also see the screen's flashing because we set the bit as 129. Now the 1 in 129 is dark blue, and the 128 in 129 is the flashing bit. And this is actually hardware flashing. Even if I crash the machine with a disable interrupt halt, I believe it will continue to flash because it's actually done by the hardware, not by a firmware interrupt. So that's quite surprising. Flashing colours aren't particularly useful, I don't think, but it's an interesting thing. And you'll see there how the bitmap data and the colour data are in 2 separate areas, albeit consecutive, and that the colours are at the bottom of the memory area. So that was my first example, and now what we'll do is we'll just close this, and I'm going to start another example. So we'll just exit that, and just bear with me a moment. I'm going to run a little script here. So here is my second example, and you'll see this is going to run off a disk image, and here is the assembly for this one, and it's basically the exact same command we did before. We're going to start at 4000 in hex, and we're going to move down the 192 lines. So we're going to start at 0 and end up 191. We're going to fill each line with the byte equivalent to that line. So you'll see how the memory is laid out on the ZX Spectrum, and I think you've already understand it. It's fairly self-explanatory. And here we've got our get next line command. Now, as I said before, the Spectrum screen memory is split into 3 chunks, and so you'll see that the get next line command is also split into 3 chunks. And I think this is where the logic comes in, and I think it again comes back to drawing characters quickly on the screen, because if you are within an 8x8 block on the screen, and a fixed 8x8 block, not halfway down one of course, then you can move down one line just by increasing the H register. You don't need to do anything other than increase H. You don't need to do any checking, and that's the fastest thing you can imagine. Now, unfortunately, as soon as you get over that 8th line, you've then got to do a check, and then you've got to do another check, and so because the 3 splits make filling the entire screen a bit of a pain, but only moving down one line if you know you're not going to go over an 8 character, one of those character boundaries very, very fast, and that can be used to your advantage if unfortunately on the Spectrum it's not the case, but if the bullets on the Spectrum in ChibiAkumas were just 2 pixels, then, and I knew that they would not go over the line, I could do it without any complexity at all. It would be brilliant. Unfortunately, I've actually had to make them bigger because of the lack of colours on the Spectrum, makes them unclear. But as I say, in theory, if you're working in 8x8 limits all the time, this gives you the fastest next line you'll ever get. And one slightly strange advantage as well is if you look at the Spectrum version, I'm using A, H and L, but if you look at the Amstrad version, I had to use D and E, so you're actually using fewer registers, albeit you are using A, but you're not using D and E. So there is the advantage there as well. That firstly, if it's a very small area you're moving around, you can just increase H, and if it's even if you can't do that, you don't have to protect D and E through the rest of your code. If the rest of your code needs D and E, well, they'll be preserved, which is a sort of side advantage. Now, anyway, enough talking about that. Let's actually see the code running. So let's have a look. So this is just my test code. It loads the data and then it waits for me to run. And there you go. So that was very, very fast. And what you can see here, you got a little bit of garbage here and a little bit of garbage at the bottom. This is just because the code is the program is returned back to BASIC with some remaining information in the registers, and BASIC's just has responded to that. A bit of sloppy coding on my test code here, but just ignore that. So, but basically what you can see here is exactly what you'd expect. Line 0 is blank. Line 1 has just got a pixel to the right. And then if you'd got a line 255, which of course the Spectrum doesn't have, then you would have that filled in here. And I probably should have shown you this before, but if I just get in my other example here and just do mode 2 and then run it. Oh no, I apologise, wrong command. If I run this one here, you'll see actually the Spectrum mode and the Amstrad mode 2 work work exactly the same in essence, and to be honest they kind of work the way you would expect. It's Amstrad mode 1 and 0 that work in a rather odd way. They don't work in the way at least I'd have expected. But anyway, I think that covers all of the screen layout that I can do at this point. So if you want more information, please let me know. If you want to try this kind of thing yourself, just have a play. Feel free to nick my code. The current releases of ChibiAkumas are available open source for download off my website. If you really want the latest code for some reason, if you want the Spectrum code, for example, drop me a mail. I'm happy to give it to you if you want it. I wouldn't release it publicly until I was reasonably happy it's finished, but if someone's really enthusiastic, just let me know. You can have it. You're welcome to that. Please leave a comment if you want me to go in a different direction and discuss other things. I am planning on doing more tutorials like this. I'm also thinking of doing some really basic, bare bones beginners, you've never used assembly before, here's how to get started videos. So if that's interest to you, please let me know. Please follow my channel because I'm planning to do those. Now, beside this, I do have a Patreon account, which I'm posting weekly updates with regards to the current in development versions of the new multi-platform ChibiAkumas. So if you want to sort of follow those, if you want to learn more about how the game was coded, how the internal memory structures of the game work, then there's a lot of sort of documents on there that I'm posting. Also, I currently have a competition running where I'm going to be giving some of my patrons free t-shirts at the end of next month. So if you want to be in a chance with winning those, please sign up and follow me on Patreon. I hope you've enjoyed this today. I hope you didn't all give up following the video when I started talking about those very confusing MSX slots. And I hope the information I've given you today is of interest and reasonably correct. Thanks a lot for following me. Bye now.